Yeah, so it's 11 o'clock. Welcome back to another session. Before we begin, please, do you have any questions for me? Any comments, any issues you need me to address? Okay, so when you look at, I have one comment though. When you look at the schedule, right? This week on Wednesday, we have, which is our next meeting, we have, it's going to be a reading day, right? Let me see, spring. That's on 10th March, right? On 10th March is a reading day. So on that day, there is no class, right? So basically what I'll be doing is I won't be taking attendance, but I'll be making a video. I'll be posting a video for the class, right? I'll be posting lectures. So you can decide not to come and just watch the recording. I won't take any, I won't take attendance on that day. Yeah, but if you also want, you can just join me as I make it. So it depends on you. You can decide to rest or join. It's really up to you, right? So no class on the reading day on Wednesday, which is our next meeting. But I'll be here to make the video using the class like link and then leave the recording for you guys. Okay, so that's the statement on that. Tomorrow, let me check the schedule and see. March 9th. Yeah, tomorrow is also a reading day. So that one too, no class. Yeah, no class on Tuesday. And then no class on Wednesday. But on Wednesday, as I said, I'll be here. On Tuesday, I think it depends on you and your TA. Maybe if you need help, you can still see the TA, but on the schedule is no class on that day. Yeah. Okay. Please, any questions on that? Okay, then let's get on to work. So last time, right, on Friday, we introduced some differentiation rules for trigonometric functions. Let me share my screen. Okay, please, I'm sharing my screen. If you can't see, let me know, right? So we looked at differentiation formulas for trigonometric functions. We saw like some two important limits, which were the limit as theta approaches 0 of sine of theta over theta. We said that was 1. And then we said the limit as theta approaches 0 cosine of theta minus 1 all over theta is equal to 0, right? So we saw these two limits. And from these two, we were able to obtain the derivative for sine, for cosine, and then we've moved on to use the quotient rule to find the derivative of the other trig functions, right? So that led to these 6 rules, right? Okay, so we wrap these up and then we're going to look at these examples. So that's where we ended the last time, right? Let me zoom. Shift 5. Okay, so I'm here, right? Okay, so for this question, this is the second example, right? We have to differentiate a function f of x, which is given by secant of x all over 1 plus tangent of x. So the solution. So I'm being asked to find f prime of x. So the first thing I do is just attach the differentiation operator to the function, right? So secant of x over 1 plus tangent of x. To make this interactive, please help me out here. What do you think? Which rule should we start with here? What do you see? What rule can we start with here? What do you think? Anybody? Which rule can we start here? Which rule happens here? As I always say, feel free to speak your mind. If you make mistakes, it's all part of the learning process. Yeah. Anybody? What do you think? Oh, okay. So it's not coming up. Yeah. So I have quotient. Perfect. Yeah, that's true. So this is going to be a quotient rule at work here, right? So you can see that this is a function here divided by another function, right? So by the quotient rule, what do? It's just low. So what is our low? Our low is the function here, 1 plus tan of x, right? So it's low d high, derivative of the high, right? So that's secant of x, minus high d low. So that's the derivative of what? 1 plus tan of x all over square of what is below. So that's 1 plus tangent of x all squared, like so. And then after this step, we just look at where the differentiation operators are attached and then get those derivatives, and then we are done, right? So moving forward, I'll just repeat the 1 plus tan of x. That one has no differentiation operator attached to it, so just repeat it. And then the question is, what's the derivative of secant of x? As I told you the last time, it would be a good idea to memorize all of these. In fact, from the department, they are not allowing you formula sheets on your exams, right? So they ask you guys to memorize. So please do try to memorize. Don't wait until it piles up, right? Don't wait. Yeah, so does anyone remember the derivative of secant x? What's that? What's the derivative of secant of x? Anybody? Or you've not memorized yet? Nobody. Okay. I see secant x tangent x. Perfect. Perfect. Thank you, Jesus. Yeah, that's true. So the derivative of secant x is secant x tangent x. So as you can see, if you don't memorize this, then you'll be stuck here. Like on an exam, you'll be stuck. So the rules are very, very important. And then minus secant of x. And then for this derivative, it's a sum of two terms, right? It's a sum with two terms. So you have to differentiate them term by term. Now the derivative of 1 is 0. And the derivative of tangent, does anyone remember what the derivative of tangent x is? Anybody? So you see, if you don't know this, then you'll be stuck here. If you don't know what the derivative of tangent is, then you'll be stuck. Yeah, so as I always say, it's very, very important. So let me see. I have some messages. The chat just disappeared. Give me a sec. Let me see if I can bring it back up.
Is it secant squared x?
Yeah, secant squared x. Thank you. Yeah. So also, it's also allow you guys can just feel free to unmute yourself. Where did the chat go? It just disappeared. What's happening? Oh, okay. Came to hide here. Okay, secant squared. Yeah, from Hunter. Thank you. So let me go back to the PowerPoint. Okay, so it's just secant squared of x, which is left here, right? And then all over 1 plus tangent of x all squared. And as I always say, when the differentiation operators get you're able to get rid of them, then you are done. So I can leave my answer here, and then I'm done. Like in the website, to accept something like this on an exam or on a test or anything, I will accept this also, right? So that's your answer. Unless maybe in your final exams when it's MCQs and I've simplified. So that way you have to work and simplify towards that answer, right? But apart from that, for the free response, you can just leave your answer like this and you are right. So that's it. You have the derivative. But feel free to, if you want to simplify, that's fine. But I'll advise that on an exam, please don't do it because you'll be wasting precious time, right? Because you can just put this in and you're right, rather than spending some minutes trying to simplify and then plugging in, right? Okay, please, any questions here? Okay, anybody needs time here? Okay, so with this section, right, chapter 3, usually when you know the rules, they are quite straightforward. If you're able to memorize them, then they are quite straightforward, right? Yeah, the rules are very, very important. Okay, so now let's look at this question. It says, find the 27th derivative of cosine of x. Okay, so now, just as we did, do you recall that we saw a question where it asked for the nth derivative? Whenever it asks for a certain number of derivative, like some position derivative, like 27, then what you have to do is try and see if that function's derivative has a pattern. If it has a pattern, then you can kind of like guess or try and figure out what that 27 to be based on the pattern, right? So for this one, we have a function f of x given by cosine of x. So to see the pattern, let's check out what the first derivative is. So please help me out here. What's the first derivative of cosine of x, right? So just attach the differentiation operator to cosine of x. What's d over ds of cosine of x is what? What's the derivative of cosine? Anybody? Derivative of cosine, what do you say?
Sine x.
Thank you, thank you. But very close, very close. You want to try again?
Very negative.
Neg.
Perfect, perfect. It's negative sine of x. Perfect, thank you. Yeah, so negative sine of x. Okay, now this is the first set. So let's see what you're going to do is let's keep repeating the pattern and see if we'll get back to cosine. If it gets back to cosine, that means the pattern will repeat itself again, right? So we won't end here. Let's try the second derivative, right? So that one's just the derivative of the first. So that's d ds of negative sine of x. So guys, what do you think? Please, can anyone help me with this? What's the derivative here? Let me put this in this square brackets. What's this derivative? What's the derivative of negative sine of x? Anybody? As I said, feel free, speak your mind, make this interactive and practice. Yeah. Anybody? What's the derivative of negative sine of x?
Negative cos x.
Negative cosine of x. Now, for negative sine of x, just ignore the negative and look at the derivative of sine. The derivative of sine is cosine, so we have negative cosine of x. Thank you so much. Yeah, so we have that one. The pattern has still not repeated yet, so let's keep going. Let's get f prime prime prime. F prime prime prime. Yeah. So that one will just be the derivative of what? D over ds of what? Negative cosine of x. Right. So for this one, what do we get? Anybody? What do we get for this? What's the derivative of negative cosine? In other words, you can just do the negative. What's the derivative of cosine? What's the derivative of cosine? Anybody?
Negative sine x.
Perfect. Thank you, Jerry. Yeah. So negative sine. The derivative of cosine is negative sine, right? So that means negative negative will be sine of x, right? So we have the third derivative being sine of x. But still, the pattern has not repeated yet. We don't see any pattern yet, right? Because this is sine of x. So let's proceed and get the fourth derivative. So for the fourth derivative, you're doing the derivative of what? D over dx of sine of x. And what is that? What's the derivative of sine of x?
Negative cosine of x.
Close. Do you want to try again? Very close.
Oh, just cosine of x.
That's true. So the derivative of sine of x is just cosine. Oh, what do you see? Nice, 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 nice. So that means that whenever you have the cosine of x, right, it repeats after every fourth derivative. Because when you start differentiating this cosine of x here, right, when you start differentiating this one, you see that it will come to negative sine of x, negative cosine, and then sine, and then come to cosine again. That means the cycle repeats after every fourth derivative. You see, after every fourth derivative. So now that we know the pattern, all that we have to do is try and guess what position this will be in the when we repeat the steps 4 times. You see. So what you can do is just do at this point, just do 27 divided by 4. And then find the remainder. And the remainder will tell you which position it is. Right? So for example, if we had no idea of, wait, let me erase this before I can erase here. Let me come here. Yeah, let me erase this before I continue with this. Let me try and put this point across. Okay, so because we repeated cosine of x, like assuming I didn't, now that I know that it repeats after every 4, assuming I didn't know, I want to still try and use the pattern to get what the derivative, the fourth derivative is, right? Then the fourth derivative, how will I compute it? The fourth derivative is just 4 divided by 4. What is that? 4 divided by 4 is 1 whole number, 0 over 4. The position is 0, right? So this cosine of x matches to position 0. Let me say position 0. And then the first derivative matches to position 1. The second derivative, the negative cosine, matches to position 2. Now this derivative, the sine of x, matches to position 3. And then the cosine repeats again, position 0. So whenever you divide, you say you're trying to find, say, the fourth derivative, you divide the 4 by the 4. It's bad I repeated the 4 here. Okay, I'll try more examples. So you divide this and check the remainder, right? Check the remainder. So if I divide 4 by 4, then the remainder is going to be 0 over 4. So what is the 0th position? So you check the remainder, position 0. So that's what? So that's how I know the fourth derivative is what? Is cosine. Now let me change it so that I don't repeat the 4 and the 4 again, so that you see what I mean. Let's look at the 27th derivative, which is what the question is about anyways. So the 27. So what I'm going to do is I'll do 27 divided by 4. And what's 27 divided by 4? Well, as you know, 4 times 6 is 4 times 6 is what? It's 24, right? 4 6 24. So 4 4 8 32. 4 6. Wait. 4 6 is 24. 4 7 is 28. Yeah. 4 6 is 24. So that's the closest. So we have 6 whole number, and then what? After 24, how do you get 27? You add 3 over 4, right? That means that we are looking for what? Position 3. And what is that? Which one fits position 3? It's sine of x. So that means that we know that f, the 27 derivative is just sine of x. Please, I hope this makes sense. Is there any part you don't understand? Okay, if you do understand this, then let me ask this. Can anyone guess what this will be? Say the let's see, the 16. No, let me try 7. Oh yeah, let's try 17. What will be the 17 derivative? Can anyone please help us with this? What will be the 17 derivative? Anyone?
Negative sine of x.
Negative sine of x? Yeah, that's perfect. That's true. Negative sine of x. Thank you. That's true. Right? Why? Because you just do the 17 divided by 4. 17 divided by 4 is 4 whole number, 1 over 4. So that means you're looking at position 1, and position 1 is negative sign. So negative sine of x. Perfect. Thank you so much. Please, any questions on this kind of question? You get something similar on your homework. Any questions? Let me add this note. Position 1. Okay, then that's it for this. Anybody still needs time? Okay, so the question is, are we always going to look for 4 positions? No, not necessarily. We are going to, if it's like a derivative which will come back to itself at some point. So suppose we're doing for some other kind of trig function, and then it repeated for, let's say, the 5th level. After the 5 derivatives, then we came back to the function. The number of steps or the number of positions will depend on how many derivatives you applied before getting back to the original. You see, so for this cosine, we did what? 1, 2, 3, 4 before we came back to cosine. That's how we know there are 4 positions. If you do it like 10 times before you come to the original, then there will be 10. So in that case, you'll be dividing by 10 and be checking the remainder for the matching position. Please, you get it? Yeah. Okay. Please, any other questions here? Okay, so that's how you do it for position matching for like higher derivative powers. Yeah, anybody needs time here? Maybe let me circle this. Let me put a box around this because this is what the question was asking for. Okay, this like multiple in one. Anybody needs time here? Okay, now let's come here. Now you realize that when we started to find the proofs for the sine, the derivative of sine and cosine, I told you that 2 very important limits come to play, right? So I told you to note these 2 limits. The limits as theta approaches 0 of sine of theta over theta equal to 1. And then the limit as theta approaches 0 of cosine of theta minus 1 all over theta equal to 0. Now, these are 2 important limits you have to know going into the second exam, right? Okay, so whenever you see a limit which involves like some sine of some radian or some radian or cosine of some radian minus 1, then it fits this structure. So looking at the question that we have here, we have limit as s approaches 0 of sine of 7x over 4x. Now, what this standard rule is saying is, if you are taking a limit of sine of some radian all over the same radian, and then that radian is approaching 0, then that thing is 1, right? So the first thing is it has to be sine of something, right? And then over the same thing, and then that thing has to be approaching 0 based on the given limit, and then it will give you 1, right? That's what this limit is saying. Now, a similar idea holds here. When you're taking the limit as of cosine of some radian minus 1 all over the same radian, so these have to match. And then the other thing is, the last thing is, it has to be approaching 0. Then if these conditions hold, then that limit is also 0. Okay, so we are just going to use this tactic to try and solve this. So I look at this, I look at this limit, I see sine of 7x. I say, okay, this one has sine in there. Okay, so it's sine of 7x. The question is, do I see a 7x down here? No. In this case, the 7x is not down here. Okay, I've not satisfied that yet. But then for this 7x, does it approach 0 as x approaches 0? Yeah, this 7x approaches 0. as x approaches 0, right? So based on this limit condition, this radian here will approach 0. So that condition is satisfied. So the sign of this thing is approaching 0. What is inside here is approaching 0. Okay, so all that we need to do is try and recreate the 7x down here. And then when the radians match, then we can say that thing will go to 1. So how do we recreate it? Well, I can just do, say, 7x up here. Shift the 4x under the 7x, and then divide by 7x again. Now, by doing this, I've not done anything to the original expression, because the 7x and 7x can cancel out, and then I get back my sine of 7x over 4x. So no change. Please, are you okay? No harm done. Okay, but then by doing this, what's the motivation? By doing this, I've been able to get the radian here to be the same thing here. And then that thing is approaching 0 for the given limit. So that means based on that, based on this rule, based on this first rule, I can say that for this limit, I know that this one can go to what? This one is approaching 1. Yeah. You see? And then I'll be left with just the limit as x approaches 0 of sine of x over 4x. And then here, the x's will cancel out, right? We use the usual limit laws we know, right? So the x's will cancel out. So you end up with something like limit as x approaches 0 of a constant, 7 over 4. And what is that? It's just 7 over 4. Right? So with this one, the idea is just try and reconstruct something similar to this. Either this, if you see this, the sign structure there, then be thinking of this limit as theta approaches of sine of theta over theta being 1. If you see cosine minus 1 structure there, then be thinking of trying to recreate the same radian here underneath it, and then that radian has to be approaching 0. If you're able to recreate it, then you can either go to 1 for the sine of theta over theta, or you can go to 0 for the cosine of theta minus 1 over theta. Yeah, so that's the idea. Please, any questions here? Later on in chapter 4, we'll be learning about the L'Hopital, but you are not allowed to apply the L'Hopital yet, you see. You're not allowed yet, yeah. So you have to use this strategy going forward. Okay, please, anybody needs time here. Any questions here? Is there any part you don't understand that you want me to go over? Okay. Okay, then let's move on to this one. So for here, we are looking at the limit as x approaches 0 of s cotangent of theta. Cotangent of x. So let's try and figure this out. This one, maybe I can make it bigger. Yeah, so for this one, I start, okay. So what is cotangent of x? Cotangent is cosine over sine. Right? It's cosine over sine. Okay. Now, I'm taking the limit as s approaches 0. Now, as you can see, for this limit, usually it will be type 0 over 0, because if you plug in 0 here, you get 0 over 0, right? So if that was your go-to, it won't work here. But then it's not like we can cancel out any common factors like we did for the previous ones. There's no way you can simplify this and cancel out, right? So that should tell you that the fact that it has trig functions there should bring your mind to those two limits. The limit of theta approaching 0 of sine of theta over theta equal to 1, then the limit of theta approaching 0 cosine of theta minus 1 over theta equal to 0. So right, so those should come to mind when you are faced with an issue like this. The limit involves trig functions, and then you can't cancel out, right? Okay, and then it has that structure, cosine of theta minus 1 somewhere in there, or sine of just theta somewhere in there. Here I can see sine of x. So I say, okay, since I see sine of x, perhaps I can do something here with this, right? And then this x here is approaching 0 for the given limit. Okay, so the x here is approaching 0 for the given limit. That's good. Okay, so what I can do here is I just need an x in the denominator for the sine of x to go to 1, for that sine of x over x to go to 1. So I'll just create it, right? So one way I can do that is just multiply the numerator and then the denominator by the same 1 over x, right? By the same 1 over x. I've not changed anything because the 1 over x can cancel out and I'll get what? S cosine of x over sine of x. So no harm done. Okay, so then after writing this out, let me try and write out what I have, right? So I have limit as s approaches 0. The x's on the top here will cancel out. That'll leave me with cosine of x. And then for the bottom, most importantly, I'll get sine of x over x. That was the target, right? The reason why I saw I was going to go for that, for the limit as theta approaches 0, sine of theta over theta, was because I don't see cosine of theta minus 1. I only see cosine of x. In other, I'm just exchanging the theta with s, but I hope you get what I mean, right? I don't see that structure, cosine of x minus 1. If I had seen cosine of x minus 1, then I will also be thinking about the limit as s approaches 0 of cosine of s minus 1 over x, right? But I don't see cosine of x minus 1. So the only thing I see is sine of x. And that one, I have to be thinking only about the limit as s approaches 0 sine of x over x equal to 1, right? So that's why, that's the motivation for targeting this, right? For doing this. Okay, so at this stage, I know that this thing, since the angle, the radian here is approaching 0 for the given limit, and then there is divided by the same x, that one go to what? Go to 1. So in the long run, I just have limit as s approaches 0 of cosine of x over 1. And now let me try plugging in again. What's cosine of 0? Cosine of 0 is 1 over 1. That is 1. So after you employ those identities, the limit as sine of the limit as s approaches 0 of sine of x over s equal to 1, or the limit as s approaches 0 cosine of s minus 1 all over s equal to 0, then whatever remains, we will use the what? The normal limit rules that we learned, right? So you try plugging in, and then you cancel out common factors if there are any, or something like that. Yeah. So that's it on that. Please, any questions here? Anybody needs time? Okay. Now let's look at this. So I put this example to illustrate the structure with cosine of x minus 1. Do you see? So right away, I see cosine of x minus 1, and I see sine of x. So that means I should be thinking of the two structures, right? I should be thinking of the two. So limit as x, let me use x and not theta so that it matches this. So s approaches 0 sine of x over x equal to 1. And then the limit as s approaches 0 of cosine of x minus 1 over x is equal to 0. Okay, so with that in mind, let me try and solve this. So I go limit as s approaches 0, cosine of x minus 1 over sine of x. So the question is, how do I recreate the sine of x over s in there? And how do I create the cosine of x minus 1 over s in there? So all that I have to do is, for the top, I have to multiply by what? 1 over x. And then for the bottom too, I can multiply by 1 over x. Now, when I multiply both the top and the bottom by 1 over x, I've not changed the original expression, because these two 1 over x's can cancel out, and I get back the original expression, right? But then by introducing this 1 over x, what have I done? Well, let's see. This is now going to become limit as s approaches 0 cosine of x minus 1 all over x. And then the denominator is just sine of x all over x. Oh, nice. What do you see? I see these structures. Now, the radian here is approaching 0 for the given limit. And then the same structure is what I see here. So that means this thing is approaching 0. That is approaching what? 1. So that means, oh, sorry, not 0. I can't erase here. Let me go back. Keep, erase. Okay, so shift 5. Yeah, so that one will go to 1. So that means in the long run, you just have 0 over 1. That's what's left, right? And that's just 0. And that's your final answer. Please, are you okay with this? Any questions? Okay. Now, if you do understand this, let me test you on this and see. So try and figure this out. Please try and figure this out. It's just a side note. Let me make a blue line here. The question is, what do you think this will be? At first, it looks intimidating, but what do you think?
1.
Perfect. That's true. It's 1. Thank you. Because we have the thing here, the sine of some radian. And then that same thing here is approaching 0 for the given limit. And then the same thing can be found here. So it's just 1. So technically, you can just replace the s squared plus x all over, sorry, the s squared plus x with like h or theta. And then you have limit of theta approaching 0 or sine of theta over theta. And that's 1. You see? So yeah, so whenever you see this, then you can just employ these two identities, like these two limit laws for the trick, and then you be on your way. Yeah, that's it. Please, any questions here? Okay, so that's it for 3.3. Yeah. Anybody needs time here? Okay. Now let me save. And then move on to 3.4. Okay, for 3.4. Now this is one of the useful rules you ever learn in calculus, and it's called the chain rule. It's called the chain rule, right? Now let's look at the motivation for the chain rule. Now, with all the rules that we've obtained, right? With all the rules that we've obtained, we've learned about the sum rule, the difference rule, the power rule, and so on and so forth. Suppose, let me go to the whiteboard and show you something. 3.4. The chain rule. So with the rules we've learned so far, suppose I ask you to find, let's say f of x is equal to, say, s plus 1 times, say, let's say s plus 1, right? So suppose I give you something like this. Well, you can use maybe two ways to do this. You can say, oh, okay, I know that f prime will just be d over dx of s plus 1 times s plus 1. So what can I do here? Well, when I get to this point, I can say, okay, this is just a product of functions. So I can employ the product rule. So by the product rule, leave one alone, apply with the derivative of the second. Well, they happen to be the same functions here, but yeah, that's the idea. So and then leave the second alone, apply the derivative of the first. So I can do this, right? And then the derivative of the second is just 1, right? Derivative of x is 1, derivative of 1 is 0. And then the same will happen for the second part. And this one is also 1. So when I'm done, I'll just get, that's x plus 1 plus x plus 1. And that's equal to 2x plus 2. Okay, so no problems. This one, I have a way of doing it with the normal rules we've learned up to this point, right? With the standard rules we've learned up to this point. We are okay. We don't need any extra rules. Okay, another person could have also said, for this f prime, when I get to d over dx of s plus 1 times s plus 1, well, the first thing the person can try is, I'll try and multiply this out. So I'll have s times x is s squared. And then I'll have s times this plus this, that's 2x. And then 1 times 1 is 1. So that's still valid. Now, when the person does this, they will say, okay, now my f prime, so this one way, this another way. The person will say, oh, now my f prime is just going to be, now I can do it the derivative 10 by 10. So I do the derivative of s squared, that's 2x. The derivative of 2x is 2. The derivative of 1 is 0. And I still end up with the same answer. No problems. So we are good. But then the problem is, what if I ask you for something like this? What if I say, let me call it g of x. What if I say g of x is equal to, say, s plus 1 to 1,000? Okay. So with the rules that we have, looking at the first approach or the second approach, well, the product rule doesn't seem to going to be very helpful here. Because are we now going to break this s plus 1 into 1,000 terms before we do it 10 by 10 for each of them, or what? We can't, this one won't be feasible. Neither with the second one, right? Well, technically you can use binomial theorem to expand this, but it's still not going to be convenient. So how do we deal with something like this, right? So for this case, you can neither use the first approach or the second approach comfortably. So that's why we need to extend on the rules we've learned so far. So that's why we need something we call the chain rule, right? We'll see why we call this the chain rule very soon. But I have to go to the whiteboard to show you more on this. Anybody needs time here? Okay, so then let me go here. So when you come here, what this is even proposing is, Suppose I give you a f of x equal to a square root of s squared plus 1, right? This is the same as s squared plus 1 all to the power half. So for this, with the rules that we've learned so far, how do we differentiate this? You can't break this into like 10 by 10 and do it 10 by 10, unless you use the binomial theorem, which is going to be very complicated. Or how do you even multiply this out? Like with the rules that we have, you can't do this conveniently, right? So that means you are stuck. But then the chain rule is saying that if you are able to see that function as a composite function, right? So if you recall from your earlier math classes, a composite function happens when you have something like f of g of x, when it's like f g of x. This is what we call a composite function. It is a function plugged into another function, right? So g of x, f of x is evaluated at g of x. So a function in a function, right? This is a composite function. So that's what the chain rule is saying. The chain rule is saying if you're able to define, identify that function you're about to differentiate as a composite function, then what you end up doing is, so the derivative of, maybe let me write this directly first. So this one, there are two notations, but you use one in the long run. So what the chain rule is saying is, whenever you are able to identify the function you're about to differentiate as a composite function, all that you have to do is, to simplify matters, differentiate the outer function, and then evaluate at the inner function, and then multiply by the derivative of the inner function. This is called prime notation, right? So that's what the chain rule is saying, right? So this is saying that if you're given f of x equal to square root of s squared plus 1, well, I can see that, okay, this one looks like two separate functions. There is an s squared plus 1, which is being plugged into square root of x, right? Because if you give, like, if you define a function, say f of u, to be square root of u, and then you define some other g of s function to be s squared plus 1, then when you do the composition, which is f evaluated at g of s, it is just going to be a plug the g of x into f, right? So that would be a square root of what? S squared plus 1. You see? So that means for this, we can see it as a composite, as a composition, where the outer function is something like square root of x, and then the inner function is s squared plus 1. Please, are you okay? So the ability to utilize the chain rule is to be able to distinguish between what is an inner function and what the outer function is. Okay, so more on this, right? Now, as I was saying, whenever it's a composite function, we can use the chain rule. But there's also another notation. I thought about this man, Gottfried Leibniz, as one of the fathers like the fathers of calculus, right? Those credited with calculus. He has this Leibniz notation, right? This in Leibniz notation. But you'll be using one notation entirely, right? You won't be talking about this. I'm just going to give you this for information purposes. Okay, but I'll need to move on to the next slide, right? So this is summarizing everything. So what this is saying is, if g is a differentiable at x and f is differentiable at g of x, and then you have a composite function, so some outer function and then some inner function, right? So this is an inner, and then that's an outer. So if you are able to identify some outer and an inner function, then what the chain rule says is, this, using the prime notation, just differentiate the outer function, plug in the inner function, and then multiply by the derivative of the inner function. So that's the chain rule. Or in Leibniz notation, the Leibniz notation is similar to this. All that is saying is, instead of doing this directly like this, just define the outer function to be f of u, and then define the inner function to be g of x, right? So let u be the inner function. Then if you want the dy over dx, which is the same as the f prime, right, the uppercase f prime, then just do dy over du. So your y will be expressed in terms of u. So just do the differentiate that with respect to u, and then multiply by what? Du over dx, right? Du over dx is representing the second function. So you have u to be your dependent and then your s to be your independent. Well, you can think of this as the magic that is happening here is the du's are canceling out, and then you get dy over dx. They don't actually cancel out, but one way to see it is, this is what is happening, right? But I'll show you, I'll illustrate it on the example you're going to see very soon. Please, I hope you at least you get the idea. So this is used for composite functions, a function inside a function. So if you identify that, then you just differentiate the outside function, plug in the inner function, multiply by the derivative of the inner. That's it. Okay, so I think you appreciate it more after seeing some examples. But do you need time here? So this is what we'll be using. Using this. You use Leibniz notation for this class. Use this for this class. That one is simpler. Okay. Anybody needs time here? Okay. So perhaps let me add this. So do you remember the example I showed you earlier on? That one was s plus 1, s plus 1, right? So for this one, f of x is the same as s plus 1 all squared. So we can say, okay, what is f prime? So we attach the differentiation operator to this s plus 1 all squared. And then we say, okay, for this one, can't I use, this is a composition, right? S plus 1 is my inner function. And then my outer function is something like s squared. You see, it's like x to the power 2. So what is the chain rule saying about this? Well, the chain rule says differentiate the outer function. So how do you differentiate s squared? You're going to use the what? The power function. So by the power rule, what do we do? Bring the power up and then subtract 1 from the power. But don't forget that you don't have to, you shouldn't write x here. You are plugging in the inner function. That means I have to plug in s plus 1, which is the inner, and then multiply by the derivative of the inner, s plus 1. So what is this? That means this is going to be what? This is to the power 1, so that's still going to be 2x plus 2. And then the derivative of this is 1, right? And isn't this the same answer that we got? It's the same thing, right? But the power in this is, suppose we have g of x, which is the one I gave you, x plus 1 to the 1000. Then for this one, if you use the chain rule, you attach the differentiation operator, d over dx. Oh, it's not writing. Let me get out here. So d over dx, okay, it's back on. Oh no, shift 5. Yeah, so d over dx and then what? S plus 1 all to the 1000. So I say, okay, I know I can't multiply this out, but is this a composition? Yeah, this is some inner function and then that's an outer. So by the chain rule, differentiate the outer function. The outer function looks like s to the 1000. So that's a power rule. So I have to bring the 1000 down. Don't write x there because you'll be plugging in the inner. And then subtract what? 1000, you subtract 1 from the power. And then multiply by what? The derivative of the inner. First, let's plug in the inner here. After doing this, multiply by the derivative of the inner, s plus 1. So what do you get? You get 1000 and then s plus 1 to the 3 nines, right? 1, 2, 3. And that's it. I'm done. Please, I hope at least this makes sense a little. We'll be doing more examples, but yeah, that's the catch. So at least you see the power of the chain rule. It's a very, very powerful technique. Very, very nice technique to know. Yeah. Any questions here? Anybody needs time? Okay. So if you're able to identify something as a composite function, then just employ the chain rule. Okay, so if you don't need time, let's do some proofs. I said it's a good idea to see the proofs and know that you're not just generating anything from anywhere, right? So suppose I give you this. This is a composition, right? How come the chain rule says do the derivative of the outer function, plug in the inner function minus what? Do the derivative, multiply by the derivative of the inner function. Okay, so let's try and get f prime. So using the definition of the derivative, this limit as h approaches 0 of uppercase f of x plus h minus uppercase f of x all over h. So this is going to be limit as h approaches 0. And then for uppercase f of x plus h, it's just going to be what? F of what? G of x plus h. Right? And then we have minus, then for this part, we have f of what? G of x. And then all over h. Please, are you okay up to this point? Any questions here? Okay, so after we obtain this, well, one thing we can do is, let me write this here. Okay, so we have f prime of x equal to. Now, I can just do limit as h approaches 0. Let me bring, so f plus h. And then if I add, so let me add minus g of x, and then plus g of x. Then minus, what's the time? 45, okay. F of g of x all over h. Please, you agree with this? Are you okay up to this point? Okay. So now, what I'm going to do here is, if I let, so suppose I let u to be equal to g of x plus h minus, say, g of x, right? So if I let u be g of x plus h minus g of x, I'm not going to change everything from h to u, right? So if u is equal to g of x plus h minus g of x, then as h approaches 0, then u will approach what? It's more like plugging it in. So you get g of x minus g of x. So u will also be approaching 0. Please, are you okay on this? Okay. So now, if you agree with that, then for this, I have f prime of x equal to the limit as h approaches 0. And then I have f of, at this point, I'll have, since I have u to be equal to g of s plus h minus g of x, right? Then that means that for this function, I have f of what? U plus g of x. And then for this side, I have minus what? F of g of x. That would just be, since, okay, yeah, so I can just do this, g of x right here, yeah. And then all over what? Now, I'm changing everything to h, right? I'm changing everything to h. So if I have u to be equal to g of x plus h minus g of x, then what is h? Changing this to u, right? So that's where there'll be a equation which we have to add here. So let me see, for this one, by constructing this, I have h down here. No, wait, give me a sec. Let me erase the u from here. So this h approaching 0. Where's the draw? Come on. Okay, erase. Okay, so as the h approaches 0, we have u approaching 0. Okay, and then for the h, I can just create the h from here. Okay, so h, okay, so bring the h down. And then what do we have? So this u plus u. So I have to bring the u down here and then the u up there. Okay, so here at this point, right? Where am I? Yeah, so right here, yeah, u approaching 0, g of x. Okay, so I can just bring the u here, u approaching 0, f of u plus g of h, and then minus f of g of x all over u times u over h, like so. Okay, and then at this point, another step I can do is, what is u? The u is g of x plus g of s plus h minus g of s, right? But then looking at this one, I'll have to move on to the next slide, right? So let me write this. Limit as a u approaches 0, and then f of u plus g of x minus f of g of x all over u times limit as u approaches 0. And then I have u over h. Please, you agree up to this point, right? The limit of a product is a product of the limits. Okay, but then looking at this structure, what do you see? Do you remember that from the standard differentiation technique, we said limits? No, there's not what I want. I hope I still have some time. So note, f prime is equal to what? Limit as h up to 0, f of s plus h minus f of x all over h, right? This f prime. So if you look at this structure, And you have limit as u approaches 0 of u plus g of x minus f of g of x all over u. Then it's as if the x here is g of x. Do you see? And then the h here is u. Comparing these two formulas. So that means that you can say that the first one, let me write this one. This first piece is the same as what? F prime of g of x. This first piece, right? This one is the same as this. Because the u is h and then the x is what? G of x. You see? Yeah, so you have this. Now the final piece is this limit as u approaches 0 of u over h. Now for here, the tactic we are going to employ is, what is u? Well, u is g of x plus h minus g of x, right? And that u approaches 0 as h approaches 0. So if I want to change everything back to h, again, I have limit as u, as h approaches 0. What is u? U is g of x plus h minus g of x all over h, right? H is here, I repeated it, u is this. I brought this back, and I'm changing the limit back to h. So I brought it here. Because as u approaches 0, h is also approaching 0. So you can just replace them. But then what is this? That is the same as what? G prime of x. So there you have it. Oh no, it's time. Yeah, so that's it for this. So the next meeting on Wednesday, you don't have to come, right? I'll be on the same Zoom link. I'll try and work on some of the rules. You can join me if you want to, right? But I won't be taking attendance on that day. Yeah. So that's all. Thank you for your time, and then see you on officially on Friday. Yeah. All the best. Yeah.
Thank you, Professor.
You're welcome.
Thank you.
Thank you.
Yeah. You're welcome.